respect to temperature. Obviously, ID is a constant. So the derivative of the log of ID over IS will be equal to 1 over IS times the derivative of IS with respect to temperature. Okay. Then the first term, obviously the log of ID over IS is again proportional to the voltage. So actually the first term in the formula on the first line is equal to the voltage divided by temperature. The second term can be understood as the product of kT over Q times the derivative of the log of the saturation current, and you can see it in the second line in smaller characters that the saturation current is proportional to Ni squared, and Ni squared in turn is proportional to B, that is a constant. You remember it contains the effective masses of the material and other constants. Then there is the cube of T, because you remember when you calculate Ni, you have a Fermi integral in which you change the integration variable, so you obtain kT over kT to the 3/2, and then you square, and you have T cube, okay? Times the exponential of minus the gap of the semiconductor divided by kT, okay? So this is a term to which the saturation current is proportional. When you take the log, of course you have the log of a constant that disappears in the derivation when you take the derivative. Then you have the log of T cube, and then you have minus the log of Eg over kT, that makes minus Eg over kT, okay? So when you take the derivative of all of these and you compact these terms together, you find that the gap is divided by the electron charge. So eventually one of the terms of the formula is Eg over Q, but Eg is an energy, so an energy over a charge gives you a voltage. So the ratio between Eg and Q can be indicated with the symbol Vg, that is simply the extension of the gap of the semiconductor measured in volts instead of being measured in electron volts or in joule. And then you have 3 times Vt, because when you take the derivative of 3 cube, you have 3 times T, and then you have a division by T again, so you have 3 times Vt. Now we can place numbers in place of these constants. Okay, so if you consider the case in which the p-n junction is made of silicon, and then you assume room temperature, and then you assume that the bias condition from which you start the measurement is such that the voltage across the p-n junction is near threshold, okay? You have that the value of the Vd voltage is about 0.65. It's the barrier potential, as you remember, for a standard p-n junction. Then if you consider silicon, you remember the gap is 1.12 electron volts, okay? So in voltage, as a voltage is 1.12 volts, okay? And finally, you have minus 3 times the thermal voltage that is in the range of 25 millivolts. So by 3, you have 75 millivolts. And then you have to divide by T, that is, if you take room temperature, you have 300 Kelvin, okay? So the sensitivity, that is the change in the output voltage per degree Kelvin, from this formula comes about to be minus about little bit less than 2 millivolts per Kelvin, okay? Of course, the scale of Kelvin is different from the scale of degree centigrade, but the differences are the same, okay? If you increase by 1 Kelvin, it's like you increase by 1 centigrade, because just the zero changes, okay? So we can also consider it as 1.8 millivolts per centigrade, okay? It is negative. That means that all over globally, the voltage will decrease if you increase the temperature, okay? This is one example. You remember there was another circuit, okay? Another circuit is the circuit indicated with letter B. It is quite similar because actually they use a bipolar transistor, but in that bipolar transistor, the collector is shorted with the base. So it is like one PN junction, and this PN junction is the emitter, sorry, the base to emitter junction, okay? Because the other junction is shorted. And in this case, the current generator is mimicked by a voltage generator in series with the resistance. You remember that if you consider the series of a voltage generator and a resistance, and if you consider both large, then these two elements together are roughly equivalent to a current generator. Okay? It is an easy calculation. So essentially, circuit B is conceptually the same as circuit A. In the upper left part of the figure, you can see two examples. In which on the horizontal axis you have the temperature in centigrades, and on the vertical axis you have the measured voltage. The two curves refer to two different currents forced by the current generator in series to the PN junction. Okay, you see in both cases, I mean, the slope is slightly different. In one case is -2, and the other case is -2.3. Okay. The important outcome of this analysis is that the sensitivity is reasonably linear. Okay, the sensitivity. This is the voltage to temperature dependence. Okay, so it is a good sensor. that is able to provide a voltage depending on the temperature of the material. In the next slide, we see a rather more complicated circuit. In order to explain this, I have to change the figure. But before doing that, I want to illustrate the concept. If we go back to the other type with the junction, you can see immediately, if you look at the formula on the first line on the right, that the voltage is equal to kT over Q times the logarithm of a function that also depends on temperature. Okay. So the more sophisticated circuit is based on this idea. If we succeeded in measuring some voltage that is given by the difference between two voltages of the form shown in the first line, such that when we make the difference between these two voltages, the term with the logarithm cancels, in that case we shall be able to obtain a voltage that is simply proportional to temperature, okay? Which of course is preferable, okay? So in order to do that, we need something differential. And in order to get something differential, we may consider two devices, two circuits, almost identical to each other, and then we take the difference between two voltages. Okay? So if you succeed in doing this, we obtain a device or a circuit whose outcome is proportional to absolute temperature. This goes under the under the acronym of PTAT. So a PTAT temperature sensor is able to provide a voltage that is proportional to the absolute temperature that is being measured. Now I shall change the figure. Okay, you should be able to see a page entitled Semiconductor p-n junction sensors. Okay, so if you look at the figure on the left, in particular, if you look at part A of the figure, you see that in the figure there are four bipolar transistors, Q3, Q4, and then below there are Q2 and Q1. Okay, so this arrangement of transistors is also called, for those who have previous information about circuit theory, it is a current mirror. That means that the two transistors on the upper level, Q3 and Q4, they are able to force a given current into the lower transistors. That is, Q3 forces a current into Q2, and Q4 forces a current into Q1. Okay. Then, as we shall see in the next figure, the differential measurement is carried out between the emitters of the transistors Q1 and Q2. So on the emitter of Q2 there is a resistor. So that resistor is such that we have a given current flowing through it. Okay? So the voltage across the resistor is called Vt, and of course it is different from the voltage that appears on the emitter of Q1, because Q1 has no resistor. Okay. Another issue is this, that actually in the figure you can see only one transistor Q2, but in the real circuit there are several transistors identical to Q2 that are placed in parallel to each other. So in the example of the figure here, there are 8 transistors of the type Q2, so only one is shown in the figure, but actually there are 8. So the total number of transistors equal to Q2 is called R. R is an integer that is the number of transistors of type Q2. Okay, so let's now go back to the slides. And the figure on the right shows schematically 2 transistors. The transistor on the left is Q2 or several times Q2. The transistor on the right is Q1, and on top, instead of having the other transistors that provide the current mirror, we have the currents, okay, that are prescribed. Now, if you look at the formula, if we detect or calculate the difference of the base to emitter voltage of transistor 1, that is the one on the left, and that on the right, we shall calculate the difference of 2 individual voltages that are similar to those of a diode, because also in this case you may consider that the collector is shorted with the base. So we have just the current that flows in the p-n junction formed by the base and the emitter of each transistor. These are NPN transistors, as you remember. So the transistor on the left is actually made of R transistors. So its current is R times the current of the individual transistor. So the base to emitter voltage is Kt over Q times the logarithm of R times I. I is the current in the single transistor, divided by the saturation current, that in this case it is indicated with ICEO. Instead, if you consider the transistor on the right, there is only one of them, so that what you have is minus kT over Q logarithm of I divided by ICEO. Of course, ICEO is the same because the structure of all these transistors is identical. So simply it gets cancelled out in the logarithm. Okay, so this differential structure is much more convenient because in the final result you have kT over Q, that is just proportional to T as expected, times the logarithm of R. R is the number of transistors of the type Q2 that are in parallel to each other. So in the example, R is 8. The larger is R, the larger is the signal that we can measure. Here you can see the formula, okay, that gives the voltage drop across the resistance, because what you actually measure is that voltage drop, but that voltage drop is proportional to the previous result. Why? Because if you consider, I'm pointing with the mouse, you are measuring the difference between the voltage, of VBA on the right, that is VBE, this one, and VBE on the other side. But in this difference, VB, that is the voltage of the common base of the two transistors with respect to ground, of course cancels out. And you are left with the difference of this point with respect to ground and the point on the right with respect to ground, this one, that is equal to this, that is the lower contact of the resistor. Okay, so we are actually, by measuring the drop, the voltage drop across the resistor, we are actually measuring something that is the same as before. So finally, we have a constant that is the quantity in parentheses times the temperature. So this is a much better sensor because it is just proportional to the absolute temperature. Okay. Let me check what time is it. Okay, there's still time. So let's go back to the slides. Now we examine briefly another class of temperature sensors that are of the type of the so-called thermoelectric sensors. They, instead of being based on the temperature dependence of the p-n junction current, they are based on a different physical principle. And this physical principle can easily be illustrated using this figure. You may have heard about physical effects that are called the Seebeck effect or Peltier effect. And you may also have heard about thermopiles or thermocouples. Okay. So essentially, you have a device that is made of a junction of two different types of conductors, or a combination of a conductor or and the semiconductor. Okay. For instance, you may have silicon as semiconductor and aluminum or gold as conductor, because these types of materials are easily managed in the integrated circuit technology. So using them, you can easily fabricate a device that is belongs to an integrated circuit. Okay. So if you look at the figure, assume that the pink lines are uniform pieces of silicon, and those are called A, okay? And instead, the blue lines are uniform pieces of aluminum, okay? And they are alternating, and they are connected together in the positions that are indicated by the dots. So each dot is a silicon aluminum junction, okay? You remember that when you put two different materials in contact, you have a junction and you have a barrier of potential energy for the electrons, okay? So the electrons can more easily cross the junction in one direction and not so easily in the other direction, okay? Obviously, if you consider the equilibrium situation of the system such that the two external contacts are left open, okay? There is no current in the device, but at some point you may decide to change the relative temperature of some of the junctions with respect to the other. So the typical physical appearance of the device is of the zigzag form. You see that the different pieces go from right to left or vice versa, okay? So you have a number of junctions that are on the extreme right of the page, and the other junctions are on the extreme left, okay? So assume that you change the temperature of one set of junctions. For instance, those on the left are kept at some temperature, TF, and those on the other side, on the right, are kept at another temperature, like TC, okay? The result of this will be twofold. One is that the distribution of the electrons in the two materials will become non-uniform. Okay? This cannot be explained with the simple models that we have used for describing the conduction in a semiconductor, because when we use the drift diffusion model, we assume that the temperature of the crystal is the same everywhere. Whereas in this case, the temperature obviously is not the same. It is different from left to right, okay? And changes with some law in between from left to right. So one result is that the distribution of electrons will not be uniform anymore, although originally all these pieces of aluminum and silicon are uniform. Okay? And the other difference is that the barriers will also be modified, but the modification will be different because some barriers are hotter and some other barriers are cooler. Okay? The overall result is that the non-uniform difference in the distribution of charge plus the non-uniformity of the change in the barriers will be such that we can measure a voltage difference at the two extreme contacts of this device. So delta V is non-zero when the two temperatures Tc and Tf are different. And this difference in voltage is proportional to the difference in temperature, delta T, between Tc and Tf, times some coefficient alpha AB that, of course, contains the physics of the barriers and the physics of the two different materials, times the number of pairs of the AB type that are present here. Okay, so each individual couple, silicon and aluminum, will give us some voltage drop. If we have n times n pairs or n couples, we simply add up the voltage drops and we have a total voltage drop that is easily measurable. Okay, so for the phenomenon that there are different names like Seebeck, as I said before, or Peltier, and so on. They are connected to each other. If we put some load attached to the two contacts of this structure, we obtain a current. So by forcing a difference in temperature, we can obtain a current. Or vice versa, if we force a current, we obtain a difference in temperature. All these effects have a different name, but originate physically from the same set of equations that I said before. We have 4 minutes left, so let me check what we have next. Probably we have the, yes. This is a schematic of a real structure. So if you look at the circuit, we start with the substrate of silicon. Then we grow, you see the indication N-type silicon epilayer. We grow a thin layer of silicon of the N-type that is lightly doped. And then into it, we create the channel made of P-type silicon, okay? So if then we keep all these PN junctions in the reverse bias, we do not have the current flowing from the P-type zones into the substrate, okay? The P-type zones are normal to the screen, so you can see the dashed lines like this one, okay? The P-type zone goes from the front part of the structure to the back, down there, okay? Then on top, we open contacts. One contact is here and one contact is there, and other contacts are on the other points, okay? And then first of all, we grow an insulator like silicon dioxide. So we isolate the structure that is underneath from the metal layers that will be deposited later, okay? And then we deposit aluminum strips, okay, in the zigzag form, okay? So and the contacts connect each strip to the P-type silicon below. So we have a number of metal semiconductor junctions that are like in the figure that you were examining before, okay? Of course, in this thermal circuit, there will also be some thermal resistance, but it will be small because all these lines are relatively wide, okay? So there is no delay in the reaction of the device produced by the thermal resistance, okay? So in essence, the circuit is able to react quickly to changes in temperature and provide the voltage in real time following the change in temperature. I think this is it. Okay, so we stop here. And it is exactly 6, so we shall restart in 10 minutes, and we shall start another subject. Okay.